Okay, hello. Today is lecture 10, and we will continue with the chapter 16. That is when we cause a disturbance at one end of a spring. How will this disturbance propagate? Okay, so in particular, we are interested in transverse waves. That is, if the wave is moving horizontally, how each element on the spring is moving up and down. So if I look here at point P, I will see that first it was up, then it is at equilibrium, then it is down, then it's back to equilibrium, and it will continue like this as long as the wave is propagating. Okay, we agreed that the mathematical expression of a wave is a sinusoidal function. It depends on x. Okay, so as at every position x, there is a different y. And it is dependent on t. That is, if I take a snapshot now, it will be different from this snapshot over here, different from this snapshot over here, different from this snapshot over here. Okay, plus this phase constant phi, which we agreed we get it from initial conditions. Now, the transverse speed Vy, and this is the speed of an element P. It is not the speed of sound. So here you need to make sure that you don't make a mistake with the speed of sound. So Vy is nothing but del y by del t. That is, I take the first derivative, and this will give me minus a omega cosine kx minus omega t plus 5. Okay, and if you pay attention, this a omega is nothing but Vy maximum, which is similar to chapter 15. It happens at y is equal to 0. So it happens at the very beginning. And every time y is equal to 0. So it happens here, it happens here. Every time y is equal to 0, we have Vy equal a omega. Now, the transverse acceleration Ay is del Vy by del t, or del 2y by del t square, equal minus a omega square. This is a omega square is nothing but Ay maximum, sine kx minus omega t plus phi, and a omega square is Ay maximum, and it happens at maximum and minimum positions. Okay, the second thing we discussed so far is the energy in one cycle, or the power, which is the rate of energy transfer. We agreed that as a wave propagates through a string, it will be causing some points in the string to have energy. Okay, so how do we calculate the energy in one cycle, that is in one full wavelength? It is half mu omega square a square lambda, where this mu is mass per unit length. Okay, and lambda is the wavelength of the wave. A is the amplitude, and omega is angular speed, okay, which is 2 pi f. The power, or the rate of energy transfer, power, is half mu omega square a square v. Okay, power, you just have to remember that power is E over T. Okay, so it is E, which is half mu omega square a square lambda over T, but lambda over T is nothing but lambda f, and lambda f is V. Okay, where V is the speed of sound. Also here you have to remember that, not sound, sorry, the speed of the wave. Here also you have to remember that V is equal to the square root of tension over mu. We will also be using this equation. So now we have reviewed all the material in this chapter. Let's put them all the equations are here on the side, except for V equal square root of, so let me add it over here. V is a square root of tension over mu. Okay, now let's do some exercises. So the figure below shows a snapshot of a sinusoidal wave at time equals 0 between x equals 0 and x equal 2 meters. So this is x equals 0, this is x equal to meter. The string is stretched with a tension. So I have the tension 120 Newton. And the wave function is given by y equals 0.015 sine 40 pi t minus 2 pi x plus 5. Now, where x and y are in meters and t is in seconds. Part A. Determine the amplitude A. So A, here you just have to remember that yxt, sorry. Here you just have to remember that y of x and t is equal A sine kx minus omega t plus phi. By the way, it can be kx minus omega t or omega t minus kx. It's the same thing, okay? This is not a big issue. Now, if I compare this equation to this equation, I find that A is equal 0.015 meter, okay? Omega is whatever next to t, so this is 45 radian per second. K is whatever next to the x, so this is 2 pi radian per meter. So this is part A. Part B, determine the wave, the speed of the wave v. So v is equal to omega divided by k, and this will give me 40 pi divided by 2 pi, and this is nothing but 20 meter per second. Finally, part C, calculate the phase constant phi. So phi is equal to how much? You remember, in order to get it, we have to say at t equals 0 and x equal to 0, y is equal how much? Okay, so we come to this figure. This figure is at time equals to 0. Now we have to look at x equal to 0. That is here at the beginning. Y is how much? Y is 0. Okay, so now we say y of 0, 0 is equal to, I come to this equation over here, it's equal 0.015 sine of 0, and it's equal to 0 implies, sorry, is equal to sine of phi, and this is equal to 0 implies phi is equal to 0 or pi minus 0, so or pi. Now, to decide whether it is 0 or pi, we have to, so to determine whether it is 0 or pi, we look at v of 0, 0. Okay, so we look at the velocity at 0, 0. This is the Vy at 0, 0. So first we write its equation. So Vy, this is my y. I take the first derivative with respect to time. So it is 0.015 times omega, which is 40 pi, okay, times cosine of whatever I have inside. So this is 40 pi t minus 2 pi x plus phi. Vy at 0, 0 is equal to 0.015 times pi times cosine of phi. Is it negative or positive? So here, if I look at V, is it going downward or upward? If it is going downward, implies Vy is negative. If it is going upward, like here, the wave is going upward, then V is positive. So here it is negative. Okay, and when is cosine function negative? In when phi is equal to 0 or when phi is equal to pi. So implies cosine of phi is negative, implies phi equal pi. Okay, great. So we found phi. Okay. Find the linear mass density mu. So where do we make the, let's make it here. Okay. So part D, find the mu. Before we say find mu, we say V, the speed of the wave, is equal to square root of tension over mu, implies V square is equal tension over mu implies mu is equal tension over V square, and this is equal tension. It is given 120 Newton. V, we calculated it, but I had to delete it, to erase it, so it's 20 square. Okay, and this will give me 120 over 400, and this is 0.3 kilogram per meter. Finally, calculate the rate of energy transmission, for the waves on the string. The rate of energy, it means the power, and the power, this formula over here, this formula over here, down in the table. So it is half mu omega square A square times V, which is the speed of the wave. And this implies P is equal half times mu, just calculated it, it's 0.3 times omega. Omega is 40 pi square times A square, which is 0.015 square times V, which is 20. And this gives me P. You just use the calculator. Okay, so half times 0.3 times 45 square times 0.015 square times 20. This will give 10.66 watt. Okay. So with this, we solve this exercise. Now we do another one. Okay, so the wave function of a wave on a stretched string with linear mass density of mu equal 50 grams per meter. Here you don't keep it as 50 grams per meter, so mu is 50 grams to kilograms. We multiply by 10 power minus 3, okay, kilogram per meter. Is given by y equals 0.25 sine 5 pi t minus 3 pi x plus pi, where x and y are in meters, t is in seconds. At t equals 0, the string element at x equals 0 has vertical displacement of this. So we know that at t equals 0 and x equal to 0, we have y equals 0.125 meter. And moving in the positive direction implies Vy is positive. Okay, so this is given. Determine the amplitude A. So the amplitude A is this thing next to sine. So A is 0.25 meter. The frequency F, so we know that omega is 5 pi, implies F is equal omega over 2 pi, and this is nothing but 2.5 hertz. Lambda is for lambda, so we know that K is equal to 3 pi, implies lambda equal K over 2 pi. Just a second. Which is equal 3 over 2. So this is 1 point, sorry, 3. So lambda is 2 pi over K. Okay. So this is equal 2 pi over 3 pi, and this is 2 over 3, 2 over 3, 0.66. meter. Okay, and the wave speed v is omega over k, which is equal to 5 pi over 3 pi, and this gives 1.67 meter per second. Okay, determine the phase constant phi. So we will say y at 0, 0 is equal to 0.125. This is given. And this is equal to 0.25 sine phi, implies sine phi is equal to 0.125 divided by 0.25 is 0.5, implies phi equal shift sine of 0.5, and this will give me, so on the calculator, shift sine 0.5, 0.523 radian, which belongs to quadrant 1, or phi equal pi minus 0.523, which is equal to 2.62 radian, which belongs to quadrant 2. Now we need to decide if I want the angle which belongs to quadrant 1 or which belongs to quadrant 2. Okay, so to do that, to determine which value, we look at Vy at 0, 0. Okay, so Vy at 0, 0 is, I take the first derivative with respect to time. So Vy of 0, 0 is equal to 0.25 times 5 pi. Okay, cosine of pi, and this, they said that it is in the positive y direction, so this is positive, implies cosine phi is positive, implies phi belongs to quadrant 1, implies phi equal 0.523 or pi over 6. Okay, it's the same. 0.523 is the same as pi over 6. So we got the phase constant. Calculate the tension in the string. So in order to calculate the tension, let me do it here. So we will use V is equal square root of tension over mu. I square both sides because I want the tension. So this will be tension over mu. Tension is mu times V square. Tension is equal. How much is mu? It is 50 e to the minus 3. So this is 50 e to the minus 3 times V, which we calculated it here, 1.67 square. And I get my tension to be, so it is 50 e to the minus times 1.67 square. And I get this to be 0.139 Newton. Okay, calculate the power transmitted through this wave. Calculate the power. I will do it here down. I'll use another color to make it clear. So the power, or let's use also the blue. Perfect. Power is, this is the formula. It is half mu omega square A square times V, and I will just plug numbers. So this is half. Mu is 50 e to the minus 3 times omega square. Omega is 5 pi. So this is 5 pi square multiplied by a square. A is 0.25 times V, which is, we calculated it, 1.67. Okay, and you just use the calculator and you will get the value for the power to be 0.6426 watt. Okay, so calculate the power. This is part D. And the energy transmitted in 0.8 seconds. So here you just have to remember that power, energy, is power times time. So this is equal 0.6426 times time, which is 0.8. And this will give 0.514 joules. Okay. Last but not least, let me erase here. What is the transverse acceleration, so AT, of an element of the string when the transverse velocity is 0? Okay, so here we have to remember that one, the transverse velocity is 0 implies y is equal plus or minus a. And at the plus or minus a, AT is a maximum. And this is equal omega square times a, implies AT is equal to omega, which is 5 pi square times a, which is 0.25, implies AT is equal to, you get the answer, 61.69 meter per second. Okay, so this is the end of today's lecture. If you have any questions or concerns, just send me an email and we will try to, I will try to answer you in the coming lecture. So bye-bye.